Welcome back to the Math Professors. This will be part 2 of Gaussian Elimination with back substitution. And we're going to solve a system with 3 equations in 3 variables using, Gaussian elimination with back substitution. So again, what we're trying to pull off here is I want to get like a lower triangular matrix that looks like so. So what I want is I want a 1, 0, 0, 1, 0, and then a 1. So when I write these coefficients here, right now it's a 1, a negative 1, 2, a negative 2, 3, a negative 5, 3, 0, 5. But I'm trying to get them to look like this. So the first thing I'm going to go for is I'm going to try to make this a 1. And then I'm going to make this a 0. So if you're in column 1, you tend to use row 1 to eliminate column 1. Same thing down here. If I want to make this 0, since I'm in column 1, I'm going to use row 1. And if I make this a 1, it makes it really easy to make it the opposite of, this number here. So I'll explain the method further as we work through this. So let's write this as a matrix, and then we will row reduce this thing. So 1 minus 2, 3, 9. Minus 1, 3, 0, minus 4, 2, minus 5, 5, and then 17. So now our job is to, like I said, make this a 1, this is 0, this is 0. Now this is already a 1, so that's kind of convenient for us. So in order to make this a 0, since I'm in column 1, I'm going to use row 1. And since they're already opposite in sign, I'm going to do row 1 plus row 2 is going to be my new row 2. And since I want to make this a 0 as well, I'm going to, make this opposite, this 1 opposite of this 2, so I'm going to go minus 2 row 1 plus row 3 is going to be my new row 3. Now, row 1's unchanged, so let's rewrite that. So I have 1 minus 2, 3, 9, minus 1, 3, oops. Now, in order to do this row, I'm going to use this. So row 1 plus row 2, well, 1 minus 1 is going to be 0. Minus 2 plus 3 is going to be 1. 3 plus 0 is going to be 3. 9 minus 4 is going to be 5. And now doing this to create a new row 3, minus 2 times row 1, so negative 2 plus 2 is going to be equal to 0. Minus 2 times 2 is going to be 4. Minus 5 is going to be minus 1. Minus 2 times 3 is going to be minus 6 plus 5, which is going to be minus 1. And minus 2 times 9 is minus 18, plus 17 is also minus 1. So as you can see, I got my 1, 0, 0 column. Now my next goal is to make, this a 1. And again, conveniently it is. If it's not, you can always really multiply by 1 over whatever that number is, or essentially divide by that number across the row, because we can multiply the row by a non-zero constant. So, since this is a 1, I'm going to now make this a 0. So now we go after, column 2. So make this a 1, make this a 0. So since these are already opposite sign, what I can do is I can just say row 2 plus row 3 is going to be my new row 3. So what that's going to bring up is this. So the only thing changing is row 3. So I'm going to write 1 minus 2, 3, 9. And row 2 is unchanged, 0, 1, 3, 5. Now, row 2 plus row 3, since this is 0, it's going to be 0. That's why we go, from left to right. Now, row 2 plus row 3 is going to be 0. 3 plus a negative 1 is going to be 2. And then 5 plus a negative 1 is going to be 4. So far we're good. Now I need to make this a 1. In order to make that a 1, just multiply both sides. We'll multiply that row by, a half. Because I can multiply any row by a non-zero constant. And finally what this gives us is 1 minus 2, 3, 9, 0, 1, 3, 5, 0, 0, 1, 2. Now rewriting this as the system of equations so that I can use back substitution. X minus 2y plus 3z equals 9. This is y plus 3z is equal to 5. And this just says z is equal to 2. Now, since I know z is equal to 2, I can substitute back into, this equation and then go ahead and find my y. So y plus 3, well, z is 2, is equal to 5. So 6 from 5 is y is going to be -1. And now I know y is equal to -1, so that can go into here, along with z, which is equal to 2. So I have x minus 2 times, well, y, which is going to be -1, plus 3 times z, which is going to be 2, is equal to 5. So x plus 2 plus 6 is equal to 5. So, subtracting 8 on both sides, x is equal to -3. So what we get is we get a solution of, oh, that should be a 9. That should be a 9. So that should be what? So what we get as a solution is we have x is equal to 1, y is equal to -1, and z is equal to 2. Now remember again what this represents. This system of equations here really represents three linear objects in 3 space. We're talking about 3 planes. And you can kind of think of like a corner of a room where you have one wall's a plane, another wall's a plane, and maybe the top wall's a plane. That point would be the position of that corner. Now they don't have to be orthogonal or perpendicular. Your planes can come off like slanted as well, but really this is the solution. That's the intersection of those 3 planes. So let's do one more that's not really as pretty, and we get the ones across the diagonal so quickly. And that'll do it for this one. All right, so just for some extra practice, let's put this into matrix form. So 1, 1, minus 5, 3, 1, 0, minus 2, 1, 2, minus 1, minus 1, 0. And again, what I'm trying to pull off is I want to make this a 1 first, and this is 0, this is 0. Now, boy, it would have been nicer. Let's do it this way. Switch these rows. So this is going to be, let's do it this way. Let's do this one. All right, so let's do our second example. So what I want to do is I want to put this into matrix form to 2 minus 1 minus 1 minus 1, 1, 0, minus 2, 1, 1, 1, minus 5, 0. So again, what I'm trying to do is I want to make this a 1, this is 0, this is 0, this a 1, this is 0, this a 1. So we're going to go in that order. Now, these don't always have to be 1s. You know, across the diagonal at first, like if these are, like if this was a 4 here, for instance, it might just be easier to go minus 2 times this plus this is your new row 2. So you can handle the 1s at the end, but you know, it'll work regardless. So if you just go 1, 0, 0, 1, 0, 1, it'll work always. So you can kind of treat it like more like kind of like what a computer would do. Now, the easiest way to make this a row 1 really is just try to interchange row 1 and row 2, or row 2, like, or maybe row 3 and row 1. So let's do that. Let's do interchange row 3 with row 1. And I should have labeled that. That is row 1 interchanged with row 3. All right, so now that this is a 1, I can use this number to eliminate these two, because all I can do is just use the opposite of this sign by that number. So what I'm going to do is I'm going to go minus 1, row 1, plus row 2 is going to be my new row 2. And similar, I need to cancel this 3 again. I mean this 2, and since I'm in column 1, I'm going to use this row 1. So minus 2, row 1, plus row 3 is going to be my new row 3. And let's see what we hear. Remember, what this is going to do is make it a 1, 0, 0. That's the whole goal. So row 1 is unchanged. All right, so minus row 1 plus row 2 is going to be 0. Minus 1 plus 0 is minus 1. Minus a minus 5 is 5. Minus 2 is going to be 3. Minus 0 plus 1 is going to be 1. And then similar here, minus 2 times row 1, so negative 2 plus 2 is 0. Minus 2 times, so this will be negative 2 minus 1 is minus 3. Minus 2 times minus 5 is going to be 10. Minus 1 is going to be 9. And then minus 2 times 0 is still 0. Plus minus 1 is going to be minus 1. All right, not too bad. So now our next job is to go ahead and make, you know, this a 1, so that I can use this number to make this negative 3 a 0. So doing that, I'm just going to go minus row 2 is going to be my new row 2, because I can multiply any row by a non-zero constant. So what that's going to give me is, oops, I am multiplying that by negative. So that'll be negative. So positive, that'll be negative, and that'll be negative. And then this is going to be my new row 3. All right, so now that this is the one I can use, remember, I'm trying to make this negative 3 a 0, and since I'm in column 2, I'm going to use row 2 after it turns into a 1, so this is going to be 3 row 2 plus row 3 is going to be my new row 3. So 1, 1, minus 5, 0, 0, 1, minus 3, minus 1, and my new row 3 is going to be 3 times this plus this is still 0. 3 times 1 is 3, minus 3 is going to be 0. 3 times negative 3 is going to be negative 9 plus 9 is going to be 0. And then 3 times 0 plus row 3 is going to be equal to negative 1. Now let's rewrite this as a system of equations and kind of explain what happened here. So our goal is to try to, get 1s across the diagonals and then 0s in these corners, but notice when I rewrite this as a system of equations, this says x1 plus x2 minus 5x3 is equal to 0. And this says x2 minus 3x3 is equal to negative 1. So far, which is not the problem. The problem is this last line. It says 0, x3 is equal to negative 1. And if we investigate that, 0 times anything is just 0 is equal to negative 1. And that is a contradiction. So that means When you get a contradiction, you have no solution points. That really what you can talk about is you can say that these, at least two of these planes are parallel, so they're not touching, so there is no intersection between these three planes. So there is no solution here. The next I wouldn't mind showing you is what happens if this entire line zeroes out. You know, what do infinite solutions look like, you know, with a three equations and three variables? So for the last example, let's solve this system of equations. So we have 1, 0, 4, 13, 4, minus 2, 1, 7, 2, negative 2, negative 7, minus 19. And again, the same technique, 1, 0, 0, 1, 0, 1, if we can. So since this is already 1, I can use, I want to now make this 4 0 and this 2 a 0. Now, since both these things are in column 1, I'm going to use row 1. So this is minus 4 row 1 plus row 2 is going to be my new row 2. And I need to make this a 0, so this is going to be minus 2 row 1 plus row 3 is going to be my new row 3. And what that is going to give us is 1, 0, 4, 13. Minus 4 times 1 is minus 4 plus 4 is 0. Minus 4 times 0 is 0 plus negative 2 is minus 2. Minus 4 times 4 is minus 16 plus 1 is minus 15. Minus 4 times 13, so 40 plus 12 is going to be 52 in the negative. And down here, for this one, minus 2 times 1 is minus 2 plus 2 is 0. Minus 2 times 0 is still 0. Minus 2 is minus 2. Do I have that right? Let's see, no, I'm messing that up. Let's try that again. We are in, using row 3, minus 2. I guess that was right. Minus 2 is going to be minus 8. Minus 7 is minus 15. And then minus 2 times 19. So minus 26 minus 19. Let's make sure that we have this right. That's minus 15, 2 plus 7. Let's double check this too. So for this is minus 4 row 1 plus row 2 is my new row 2. So minus 4 times that, so minus 4 times 13, which was that minus 15, but I still have to plus 7. So this is negative 45. Boom. And then the next one we have to do minus 2 row 1, so minus 2 times 13 is going to be our minus 26. Minus 19 is minus 45. Yep, I was just double checking. So what we get here is, well, now I don't really have to work any further with this. Do you notice that these two lines are the same? And you're welcome to, divide this entire line by 2 to make this a 1. But then you're going to have to, multiply it by positive 2 to make it opposite. Regardless, I can see that I can clear out a row here. And I'm going to do this way. I'm going to go minus row 2 plus row 3 is going to be my new row 3. And after I'm done with that, I'm going to go negative row 2 is my new row 2. And that's just to make row 2 positive, so I don't have to have all these negative coefficients. So we'll clear out that third line first. So row 1 is unaffected. I'm going to change that sign, and then finally let's do this part. So minus this plus this is going to be 0. Minus 2 is going to be positive 2. Minus 2 is going to be 0. Minus this plus this is 0. Minus this plus this is 0. And what we can see is when I rewrite this as a system equation, it says x1 plus 4x3 is equal to 13. This one says x2 plus 15x3 is equal to 45. And the last says just 0 is equal to 0, which is true always. So last we had 0 is equal to negative 1, or if you have 0 equal to anything that's not 0, you're going to have no solutions. But if you have an entire row 0 out, what you're going to get is a form of infinite solutions. And the way we want to write infinite solutions is we don't want to do it like a high school class where we just say infinite solutions. We want to say, well, what form do they take so that I can find maybe some solution points. So what we're going to do is we're going to parameterize this. I'm sure I spelled that right. Parameterize. Boom. Okay, so in order to parameterize this, it's really easy to kind of see what variable maybe both of these equations have in common. You can see that it's going to be x3. So what I can say is I can solve this for x1. I can say minus 4x3 is equal to 13. Sorry, plus 13. And then similar, this has an x3, so I can send that to the other side. So x2 is equal to minus 15x3 plus 45. Now x3 really acts like a independent variable for both x1 and x2. So these are going to be dependent of what I pick for x3. So then we can say, well, let's let x3 equal t, which is our parameter, which is what we call it parameterized. And then now it looks like that independent variable. So now x1 is going to be equal to minus 4, well, x3 is t plus 13. x2 is going to be equal to minus 15t plus 45. And then we already said that x3 is equal to t. So you can write these in parentheses, this, comma, this, comma, this if you want to, because remember it's supposed to represent solution points. What's nice about this is I can find maybe a couple solution points. If you ask me like, hey, do you at least know a point of intersection? Sure, I can just let t be any number I want. Let's make it real easy. What happens if t is equal to 0? Well, then x1 would be equal to minus 4 times 0 is 0, so this is going to be 13. x2, this term will 0 out, so this is going to be 45. And then x3 would be equal to 0. So, this gives us that solution point, 13, 45, comma 0. Now, it's not the only solution point. Remember, this is infinite solutions, so let's pick another one. What if t is equal to 1? Well, then now x1 would be equal to, if t is equal to 1, this would be negative 4 plus 13 is going to be 9. Y over y. These are subscript solutions. You could use x, y, z if you want to as well. It's just a choice. And so if this is 1, this is going to be minus 15 plus 45, which would be 30, and then x3, of course, would be equal to 1. So then we get another solution point that is 9, comma 30, comma 1. What's interesting is if I was plotting all these points and I put them in a three-dimensional space, these points will be a line in 3 space. So really what you can think of is one easy way to look at like infinite solutions is if you have the intersection of 3 planes, well maybe 2 planes are the same plane. So if you're looking at your wall, maybe 2 planes are one wall and the third plane is maybe the back wall, and what you get is you get a line as that solution point. Now it's not always the case. Sometimes you could have, you know, planes intersect this way and then you have another plane kind of going through it as well. So you'll have like, you know, like 3 planes slicing a common line as well. So those are the types of ways that you could have, you know, this linear equation as a solution. But again, you can get particular points if you want to as well. So it's a good place to end. Thanks for watching. Uh-oh.